In below demo, I will show you how to implement a simple panning work with cubeone by creating dimension, cube, rules, etc. First, we need to start cubeone server with a predefined start server.bat. Cubeone has two clients at present. One client is web browser by FastAPI, which we can access with URL shown during server starting. Also, we can find the URL in the setting file, cubeone.ini. In the web client, you can see all the core components of cubeone, including dimensions, attributes, subsets, cubes, views, and rules, etc. From this interface, you can manage and control each component directly. For example, when you click on the Dimension panel, the drop-down menu allows you to perform actions such as list, get, set, load from CSV, reindex, and delete. The same interaction model applies to other components as well. By clicking on their respective panels, you can perform operations like list, get, set, and delete. The last two APIs in the Rule panel allow us to view or edit rules in TM1 style. For Data panel, we can read or write data in single cell or in a batch. Also, we can load data from a CSV file, clear data for the whole cube or by slice. In System panel, we can reload data from disk into memory, or save data from memory to disk. We can show current existing dimensions by listing dimension. Since this is a new created system, so there is no existing dimension now. Also, we can list existing cube, but nothing will be found now. The second client of cubeone is Excel, which is the most popular tool used by planning users and operation team. You can copy the sample Excel macro file and customize it by yourself. During the first time to connect cubeone server from Excel, you should set the parameters UDF modules and Python path to cubeone as Excel and the app folder of this cubeone Excel program. Also, you should input right URL of the cubeone instance of yours in config sheet. We are going to demo sales planning scenario in the demonstration. There are two cubes. One is price and cost, which stores data of unit price and unit cost of each product. It has 6 dimensions: year, version, channel, product, month, price and cost measures. The second cube is named as sales plan, which stores data of sales quantity, and multiply the quantity with those unit prices and unit costs in cube price and cost to calculate P&L measures of sales plan. Cube sales plan has one extra dimension, subsidiary, compared to cube price and cost. The calculation rules for each cube are listed beside. Let's start by creating all 8 dimensions used in this scenario. They are year, version, product, channel, subsidiary, and month, plus 2 measure dimensions, price and cost measure, and sales plan measure. These 8 dimensions can be grouped into 3 categories. The first category is the simple type. For this type, only the element definitions are required. All other properties, such as element type, index, and weight, are automatically managed by the system. In this demo, the year, version, and price and cost measure dimensions belong to the simple type. The second category includes dimensions with user-defined element names, as well as explicitly defined element type, index, and weight. Examples of this category are the month dimension and the sales plan measure dimension. The third category stores dimensions information in CSV files. We can create or recreate dimensions in the first and second categories using the UDF function m1dos-dimension set. For the third category, the CSV files containing the dimension definitions are loaded through the API interface. The parameters of M1 dimension set include trigger, the dimension name, the element range, the index range, the weight range, and the parent element position in that order. Please note that all updatable Cube1 functions include a trigger parameter. This parameter controls whether the function is executed or not, and helps prevent accidental updates to the system. Now let's create the year dimension by specifying the remaining input parameters. Then we will create the dimension version. And the dimension price and cost measure. Let's take a look at the sales plan measure dimension. In the definition table, column A contains the element names and their hierarchy. Here, returns and allowances, cash discount, and volume discount are child elements of total discounts and allowances. Gross sales revenue, total discounts and allowances, and freight are children of net sales revenue, where net sales revenue is calculated as gross sales revenue minus total discounts and allowances and freight. Similarly, net sales revenue and cost of sales are children of gross margin, where gross margin equals net sales revenue minus cost of sales. Column B and column C represent the weight and the index of each element. In this structure, the parent elements are positioned below their children, so the parent position is set to down. We create the dimension sales plan measures by M1 dimension set with these settings. We can use UDF M1 dimension get to check the dimension already created by us. M1 dimension get returns all dimension details, such as element names, hierarchy, index, weight, type, and level. The hierarchy displayed through indentation. Please be note that in our cubeone, the level of n-level leaf is 0. Next, we'll create the month dimension, along with its attributes, using M1 dimension set and M1 attribute set in respectively. Now we have created the month dimension and set its attributes. Let's check whether they have been created as our expectation with M1 dimension get and M1 attribute get. If the attribute name is omitted, M1 attribute get returns all attributes of the dimension. Now let's see how to create dimension with CSV file. We can load dimension from CSV file in Web API interface. Here is the API syntax for loading a dimension from a CSV file. The overwrite mode parameter controls how the dimension is updated. When set to true, the dimension is recreated. When set to false, new elements are appended to the existing dimension. The file path parameter specifies the relative path from the instance folder to the source file. The type parameter defines the structure of the source file. Set it to hierarchy levels when the source file is in flat table format, and to parent-child when the source file is in long table format. Use item attributes and attribute types when the source file includes attribute columns. Now let's create the channel dimension. In the file dim-channels.csv, there are two columns. One column is for channel, the other column is for top level. There is no column head in this file. Since there are two columns in source file without column head, we set parameter hasHeader to false and columns in numbers 0 and 1. Also, parameter type is hierarchy levels. Paste this JSON string into the load dimension from CSV API input field in the web interface and run it. A status code of 200 indicates that the command was executed successfully. Using the list dimensions command, we can see the dimensions created in Excel, as well as the channel dimension that was just loaded from a CSV file. Also, we can check the dimension information with getDimension command in API interface. Then we use file dim-subsidiaries.csv to create dimension subsidiary. There are three columns in the subsidiaries CSV file: subsidiary, its parent level, and the top level, but no columns head. Now let's create dimension product. File dim products CSV contains four columns. The first three columns, product, product category, top, are columns for dimension, and last column, category, is for attribute setting. The first line is column head. Finally, we will create the month dimension and its attributes using a CSV file. The CSV file contains 6 columns. The first 3 columns define the dimension structure, while the remaining 3 columns, Prev, Next, and Chinese name, represent attributes. To avoid overwriting the month dimension created earlier, we name the new dimension month with attributes. We can also create attributes using Excel. Here is a sample. In this example, we will create 2 attributes for the sales plan measure dimension: report and accrued. To do this, we add 2 new columns to the file and enter the corresponding attribute values. Both attributes are of string type. The function M1 attribute set is used to create attributes for a specified dimension. Now let's verify that the attributes were created successfully by using M1 attribute get to retrieve their definitions. Please note that when no attribute name is specified, all attributes for the dimension are returned. A subset is a meaningful selection of elements within a dimension, and it is widely used in TM1 and other OLAP servers. Similar to TM1, cubeone supports both static subsets and dynamic subsets. In cubeone, dynamic subsets support simple expressions only, such as report equals as and account type equals revenue, department in sales, marketing, or level equals 0. To keep things simple, MDX-based subsets are not supported at this time. Please note that in cubeone, comparison operators follow Python syntax, rather than the TM1 expression format. Let's create a few subsets for the month dimension as an example. In this demo, we will create 4 subsets for month. 3 of them are static subsets, and 1 is a dynamic subset. The names and definitions of these subsets can be found in the worksheet. First, we create the static subset default. Next, we create the static subset year and quarter. Then we create the static subset year and month. Finally, we create the dynamic subset month only by setting the expression level equals 0. Using M1 subset list, we can view all existing subsets. And with M1 subset get, we can retrieve the definition of a specific subset. Here are a few more examples of dynamic subsets. In this demo, we will create dynamic subsets for the sales plan measure dimension based on attribute. First, we create a subset named P&L, which includes elements whose attribute value equals P&L. Next, we create a subset called credit accounts for elements whose attribute value equals CR. Same we do for the debit accounts subset, which includes elements with an attribute value of DR. Now let's list the subsets just created. Also, we can display the elements within the subset with M1 subset get. Now, we have completed the creation of all dimensions, along with their attributes and subsets required for this demo. Next, we will move on to creating cubes and views. In this scenario, we need two cubes, price and cost, and sales plan. You can find their associated dimensions in the diagram on screen or in the worksheet. Creating a cube is straightforward using M1 cube create. The key point to watch out for is to keep the dimension order aligned with your design. Okay, cube price and cost and sales plan have been created now. Let's check them with M1 cube list. And retrieve their information with M1 cube get. A view is a business-oriented slice of cube data widely used in OLAP systems like TM1 for analysis and reporting. Let's walk through an example of creating a view for the sales plan cube. A view definition consists of several key parts: rows, columns, and slicers, also known as titles. These definitions can be found in the worksheet. In Cube 1, these three parts follow the same definition model. Each of them can be defined using a single element, a list of elements, subsets, or a combination of elements and subsets. This is slightly different from TM1, where each slicer allows only a single element to be selected. To distinguish a subset from an element, we specify a subset using the format dimension, subset. When a slice is defined with multiple values, such as multiple elements or subsets, the value displayed in the view is the consolidated result of those elements. If a slicer is left blank, or explicitly set to all, it means the slicer includes all leaf-level elements or the top-level consolidation, such as all products or total year. We can create a view using the function m1 viewSet with the specified cube name and view name. Okay, let's verify the view just created with m1 view list. Also, we can use m1 view get to retrieve the information of specified view. Cube1 only stores the view definition in the system after creation. It does not trigger any calculation until the user requests data, for example by using m1 view read or other data retrieval commands. Cube1 supports multiple methods for loading data into a cube. In this demo, we will focus on loading data from a CSV file, which is the most commonly used approach in real practice. In addition, this method is easy to be extended to other data sources, such as Excel files or databases. We will use the API interface to demonstrate how data is loaded from a CSV file. Let's start by reviewing the syntax. If has header is set to false, we use column numbers to reference columns. When overwrite is set to false, the incoming data is accumulated on top of the existing cell values. The mode can be wide or long, which defines how the data is structured. Wide format spreads values across multiple columns, while long format stores one value per row. Columns that should be ignored are specified in Ignore Chart Columns section. Columns with fixed values that do not appear in the source file can be defined using Constant section. Derived columns and their calculation formulas are defined in Transformation section. Here, we provide several examples. The Fixed Dimension section defines the mapping between dimensions and CSV columns, as well as constants and transformed columns defined earlier. Finally, Measure Talk Dimension and Measure Mapping specify the measure dimension and the corresponding elements to which the data will be loaded into. Next, we will load data into cube price and cost using the file cubeprice and cost.csv. The first four columns, product type, version, channel, and month, map to the corresponding dimensions. The last two columns, unit cost and unit sale price, map to the relevant elements in the price and cost measure dimension. In the JSON configuration, overwrite is set to true. We also add a new column named Year column with a constant value of FY26, which is mapped to the year dimension. We then copy this JSON into the API interface and execute the command. As shown here, the command runs successfully, with 7,408 values written into the system. Next, we will load data from the file cube sales plan.csv into the sales plan cube. As we see from file, it contains columns for both dimension mappings and sales plan measure data. Here is the JSON of load cube from CSV. First, overwrite is set to false, since we need to accumulate the data for different staffs. Second, the sales staff column needs to be ignored during the load. Third, the year dimension is not provided in the file, so we need to set it as a constant input. Fourth, the order date column needs to be transformed into order month to align with our dimension definition. Finally, we map all dimensions and measure elements in the sections in the following JSON. Then copy this JSON into the API interface and execute. The system runs successfully with status code 200 and message of 16.1.90 values written into the system. In addition to loading cube data from CSV files, Cube1 also supports loading data from a specified range in an Excel worksheet using M1 range write, and load data in view format using M1 view write. In this case, all elements used in the rows, columns, and slicers must be leaf-level elements. We have loaded data into the cubes. Now, let's have a look at these data. Using M1 view read, we can retrieve data for a slice in batch mode, instead of querying cell by cell. M1 view read supports both ad hoc views and saved views. An ad hoc view is defined directly within the function by specifying rows, columns, and slicers, while a saved view refers to a view that was created and stored earlier. The definition of an ad hoc view is totally the same as what saved view. Row, column, slicers are three major parts to be set, and they follow the same definition model. First, each of them can be defined using a single element, a list of elements, subsets, or a combination of elements and subsets. This is slightly different from TM1 for slicer definition, where each slicer allows only a single element to be selected. To distinguish a subset from an element, we specify a subset using the format dimension, subset. Second, when a slice is defined with multiple values, such as multiple elements or subsets, the value displayed in the view is the consolidated result of those elements. Third, if a slicer is left blank, or explicitly set to all, it means the slicer includes all leaf-level elements, or the top-level consolidation, such as all products, or total year. Now let's use M1 view read to retrieve data for an ad hoc view with row, column, and slicers defined above. All elements of the product dimension are displayed in the rows, because product dimension is left blank in row definition. The columns include total year and the 12 months, because the column range is defined to use the year and month subset. By adjusting the slicers, we can control and refine the data displayed on the screen. For a saved view, we specify the view name in the row parameter and leave the column parameter blank. The filter parameter can also be removed or remained to apply additional criteria on top of the saved view definition. If the filter parameter is not set blank, the filters will be add upon saved views when retrieving data. We have demonstrated the direct usage of M1 view read. Now let's look at how to create a more flexible data display with the help of Excel formulas. This worksheet shows a grid view for data from the price and cost cube. Column A lists all the dimensions of the cube. Columns B and C allow you to select an element or a subset for each dimension. Columns E and F are used to define whether a dimension appears in the row or column area, and to specify the order when multiple dimensions are used. Columns G, H, J, and K represent the calculated row range, column range, and filter range. These ranges are derived from your earlier selections and are passed directly into M1 New View Read. We can set multiple index for row or column. When the zero suppresses true, then all zero row or column will not be displayed. Okay, let's return to the data worksheet for the price and cost cube. If we examine the data carefully, we can see that the values in cells B13 and B14, which represent the unit sales price and unit cost for the total year, are incorrect. Currently, these values are calculated as the consolidated sum of all 12 months. However, as we know, unit prices should be calculated as the average of the monthly values, not the sum. To address this issue, we need to write cube rules to perform the correct calculation. A cube rule is similar to a formula in Excel, but in Excel we would need to write the formula in every individual cell, which increases both maintenance effort and the risk of data inconsistency. In contrast, by defining the rule at the cube level, we can apply the calculation consistently to all relevant cells with a single rule statement. We will use temporary variables unit price hold and unit price count to calculate the average unit sales price in consolidated cells. Similarly, the temporary variables unit cost hold and unit cost count will be used to calculate the average unit cost in consolidated cells. Let's highlight the cells that will be affected by the rules for easy observation. The rules for the price and cost cube are shown on the right bottom of the figure. For consolidated cells, the unit sales price is calculated by dividing unit price hold by unit price count. The same logic applies to the unit cost calculation. We input above rules for the cube price and cost in Edit Rule Raw of API interface and run it. Let's return to the price and cost cube datasheet to review the impact of the rule. Please remember to press Shift plus F9 to refresh the worksheet. Next, let's move to the Sales Plan Cube datasheet. Although data has been loaded for some accounts, several accounts are still blank. For example, gross sales revenue, cost of sales, margin ratio, unit sales price, and unit cost. We will highlight these accounts to observe the effect of the rules. The rules for the Sales Plan Cube are shown in the top left of the figure. The unit sales price is retrieved from the price and cost cube and multiplied by quantity to calculate gross sales revenue. At the consolidated level, the average unit sales price is calculated by dividing gross sales revenue by quantity. The same logic applies to unit cost and the calculation of cost of sales. Margin ratio is calculated as gross margin divided by gross sales revenue. Copy the rules and run it in API interface. Then we return to Datasheet of Cube Sales Plan. Press F9 to refresh page. We can now see that the values for the remaining accounts are populated through calculations. Now that all calculations in the demo are complete, let's take a few minutes to validate the results. All right, up to now, we have walked through all the key components of Cube 1, including dimensions, subsets, cubes, views, and rules, etc., and use them to make multidimensional analysis. Now we come to the final and most critical step in the planning process: writing data back to the system online. This is what truly differentiates Cube 1 from a traditional read-only OLAP analysis system. Similar to TM1, Cube 1 allows planning users to review data and directly input or adjust planning values in the system. In addition to view-level reading and batch writing, Cube 1 also supports cell-level read and write, which is the most common interaction pattern for planners. For cell-level reading, Cube 1 provides the M1 read function, also known as M1 get or DBR. For cell-level writing, we use M1 write, also called DBRW. We intentionally reserved name of DBR and DBRW to stay consistent with TM1. The M1 write function is very easy to use. Just simply specify the cube name, followed by the element names for each dimension, in the same order as defined in the cube. The function then reads from or writes to the corresponding cell in the cube. For example, as planners, if we are not satisfied with the unit sales price or unit cost for January, February, or March, we can directly enter our own adjusted values. When updating a cell, please make sure that all elements referenced in the M1 write function are leaf-level elements, as only leaf elements can be updated. After all data has been entered, press Shift F9 to refresh the entire sheet to keep all values consistent. Now let's move to the sales plan data sheet. Here we can adjust the quantities for January, February, and March in the corresponding cells. And then press Shift F9 to refresh the entire page. Okay, the data has been refreshed with the adjusted quantity of Jan, Feb, and Mar. Let's take a few minutes to validate the accuracy of the results. Finally, let's add a little bonus. Cube 1 stores its data in Parquet file, which can be directly opened by third-party analytics tools like Power BI and Tableau, a feature that TM1 does not provide. Let's take a look at how this works in practice. We generate a new column for the date using the year and month input columns. For easier analysis, we also convert the long table into a flat table by pivoting the data. However, it's important to note that as an in-memory OLAP server, Cube1's data files only store leaf-level data. Other data, such as consolidated level values and results calculated by rules, are computed in memory only when accessed by the user. As a result, these values are not stored on disk. To analyze the full dataset, you need to use the appropriate API to extract the in-memory data. When it comes to extracting data, you can use the API to download all or part of a cube's data. This is the syntax of the Extract Data API. The filter parameter works the same way as the title parameter in setView. It can be a combination of elements and subsets. If the filter of a dimension is set to null or all, or the dimension is omit, it means all elements of that dimension are included. Output format defines the output file format. Currently, it supports JSON records, JSON compact, and CSV. File folder specifies the output directory. The system will automatically generate data files in that folder, with file names starting with cube, while cube name. Two other important parameters are C-level included and rule calc included. If C-level included is set to true, consolidation level data will be extracted together. Otherwise, only N-level data is downloaded. If rule calc included is set to true, data calculated by rules will be included. If set to false, only physical data is extracted. When both parameters are false, the system simply reads directly from the Parquet data files, which makes the extraction extremely fast. If you need additional data, such as rule calculated values or consolidation level data, you must use extract data method, because this information exists only in memory and is not stored in the Parquet files. One important note: when extracting large volumes of data, we strongly recommend using filters to limit the data slice. For very large cubes, avoid downloading the full dataset. In practice, third-party analytics tools often provide their own calculation capabilities, such as DAX and joins in Power BI. So it is usually unnecessary to extract those data, especially for consolidation data. Now let's look at two examples. First, we will export all the base-level data for the cube sales plan. Okay, then let's export base-level data, both physical and rule calculated, for cube sales plan with some filters. To make it easy for data analysis with third-party tools, CubeOne also provides the Extract Hierarchy API. This API helps convert dimension hierarchies and attributes into flat, star schema files that are easy to consume by BI and analytics tools. The Extract Hierarchy API can be applied to a single dimension or to an entire cube, allowing you to download the structural information of all dimensions used by that cube. Okay, we have finished our demonstration of the basic operations of CubeOne. Thank you for watching. We hope this walkthrough has given you a clear understanding of how to use CubeOne to support flexible modeling, analysis, and planning in real-world scenarios. Last and most importantly, visit our website now, download CubeOne, and experience it firsthand.